Thank you very much for the introduction. I might get a little bit of background noise. I hope it's going to be okay. So thanks for giving me the chance to present what I've been working on for the last while. What I'm going to be talking about is a little different from the book, from the neutrinos or nuclear physics or missiles or emerging technologies or anything like that, but it has to do with the resilience of the food supply chain, which we all depend on, right? In particular, the importance of modeling the food supply chain during a pandemic. I will be talking in particular about modeling the dairy supply chain. That said, I'm not an expert in dairy. I'm still a student of the dairy field, which is actually very complex science. And I've benefited a lot from collaboration with these experts that I list here from UC Davis, and with, of course, with Rich Pilch at CNS in DC, and from Dr. Mirza at Subchain Era in Singapore, who's been extremely helpful with the software, and he's been amazing. Indeed, what I'm going to be talking about is relevant for any supply chain, including PPEs, right? Vaccine delivery, or semiconductors. Thanks also to CNS for letting me go down this unusual path of research. So also thanks for joining me over lunch. One good thing about Zoom is we can all eat comfortably in your home, the loudest foods you want, right? And I brought milk as a prop, which is appropriate for the dairy field. So I'm going to be talking about that. All right. Okay, so first I will talk about some motivations for this study. It's a bit of a lengthy introduction, and I hope you'll allow me to do that. And then I will discuss specifically about the digital twin approach. And finally, I will discuss some kind of preliminary results and some of the challenges that we've encountered. So let me start by discussing the importance and the complexity of supply chains with some kind of very recent examples. We start with this picture from Texas back in January. This was the scene from at the time. The problem was that there was this massive power outage, which caused a serious logistic conundrum, right? Supply chain is about logistics. On the one hand, health officials were scrambling to find people to inject because 8,000 doses of the Moderna vaccine was at risk of spoiling. And on the other hand, people were desperately being told to stay at home to prevent accidents. The confusion of what to do is a vaccine supply chain and logistic nightmare, which was, really illuminating for me. And I don't need to say more than just show you this picture, the importance of supply chain. I also want to talk about this example, which is called chips for cars. It just sounds nice. The pandemic and the insatiable appetite by all of us who are at home to purchase exercise equipment, laptops, microphones, etc., plus the trade war with China, plus some other unfortunate incidents, which was a fire in I think it was a semiconductor plant in Japan, and then there's also the incredible I think it's 160,000 liters or something of, I'm sorry, I might not have the right numbers, so don't quote me on the numbers, but the company TSMC in Taiwan uses a lot of water for their semiconductor manufacturing, and there's kind of a drought right now in Taiwan. So all of these problems combine make for a very serious shortage in semiconductor supply. And the semiconductor supply chain ecosystem is incredibly complex. The chips are often designed in the US, but produced in Taiwan or Korea. The chemicals are often come from Japan, and the Netherlands has basically a monopoly on high-end semiconductor manufacturing equipment. And don't forget that the software used to design the chips is almost exclusively US technology. So they're all very integrated, and it's a very complex ecosystem. The company Accenture recently did a very interesting study and found that, and this is a quote from them, components for a chip could travel more than 25,000 miles by the time it finds its way into a product. Chip-based products could cross international borders approximately 70 or more times before finally making it to the end consumer. Wafer production has about 40 countries involved in the supply chain. So any disruption to this kind of supply chain could have very serious adverse effects on the industry. And it's important to be prepared for any kind of disruption. All right, so back to the pandemic. Finally, the lack of masks and PPE. The lack of access to masks and PPE and the flawed messaging not to wear masks, even improvised ones, were one of the really catastrophic failures that has led to countless needless deaths. An editorial by The Lancet claims that 40% of the public could have been saved if masks would have been worn. Lack of masks and PPE was one of, for me, the most shocking. And here's a quote by Mary Turner, who's the president of the Minnesota Nurses Association and an intensive care nurse who works with COVID-19 patients. This is what she said in March 27, 2020. In most of the hospitals, nurses are wearing their N95s for 5 shifts of up to 60 hours, says Mary Turner, president of the Minnesota Nurses Association. It's becoming the norm to not wear N95s the way they're supposed to be used. That was March 27, 2020. Okay, I lied. The quote was actually from January of this year. So just as the Biden administration started to take over the failed response, there's still problems with supply chain with N95 masks and equivalent masks. So this was a severe failure of supply chains, among other things. So back in January, February, when I saw early on what was happening and was starting to get more and more nervous and frustrated with statements from the Trump administration, I thought about what I could do. So as a physicist, I did the only thing that helped me make sense of the situation, which is basically to calculate everything about the pandemic. So I started to do, mathematical modeling of the pandemic using rather simplistic epidemiological models and predicting what would happen in California in terms of hospital beds, etc. I also advised Ms. early on, as much as I felt relevant to my expertise, of course, physics of aerosols, etc. And then I made this page to try to warn people that we were going to run out of beds soon in California. And I was, that really got me into this path, I guess. So I was shocked, as so many of you were, about the lack of understanding about exponential growth by politicians. When the former president said of the pandemic that it's going to disappear one day, it's like a miracle, it will disappear, he blatantly contradicted what was known at the time about the virus just based on the math. He also set in motion a set of events entirely predictable that at one point the number of cases would exponentially increase, making it very difficult to control. And I still think the lack of understanding about exponential increase by politicians and policymakers is really one of the most important lessons learned from the response to the pandemic. And we will have to really think about that, what we do about this. So what happened next from February to May? Well, stay-at-home orders led to Depression-era levels of unemployment. In some parts of the country, the unemployment rate of the Great Depression was 24.9%. The national peak of the Great Recession, right, 2010, a decade ago, was 10.6%. And now the national peak due to COVID-19 pandemic was in April 2020 at 14.7%. To put that into perspective, the unemployment rate rose higher in 3 months of COVID-19 than it did in 2 years of the Great Recession of 2010. In terms of state unemployment rates, California February 2021 seasonal adjusted rate of unemployment was 8.5% compared to a Depression-era value of 16.3% in May 2020. So you see how that has rapidly changed, thank goodness, to some of the strong responses by the government and so on. In Hawaii, the rate is now 9.2%, which is 40% of what it was in May 2020. And Nevada is now 8.3%, which is 30% of the value back in May. So this unemployment had a catastrophic effect on food insecurity in many areas. We all remember these awful pictures of people lining up to receive food. In this case, 6,000 families lined up in San Antonio for a food distribution event April 10th, 2020, so 1 year ago. People were food insecure that never had this problem before. Independent people who normally donate to food banks were left to receive donations themselves. How could this happen in the United States? So we saw in February how there was this surge in demand for everything from dairy products to toilet paper, and then suddenly collapse in demand by restaurants, school programs, etc., as the country shut down. We saw then that milk was literally being dumped, right? The problem is and I'm learning this as a student of the dairy industry, the problem is cows are not machines. You can't simply turn off the production of milk. You can modify the production by changing the type of feed, but that's something that will affect the cow for a very long time. So cows, you don't want to do that. So cows don't care about the demand. They just keep on producing. The milk processors do care about demand. So as demand increases, or as demand decreases, it was not profitable for the processors to take on more milk. And so the dumping of food was occurring despite the unprecedented lines for food banks for those very dairy products, right? This very important dairy product. Then in April, Rich contacted me about whether I would be interested in helping to model the effect of the pandemic on the food supply chain. And I became totally absorbed by the topic. As anybody who knows me, I usually do. And especially when I saw the image of all these people lining up for food, I suppose we'll all remember that. So that was a very long introduction, and I'm sorry about that, but I wanted to kind of situate where I'm coming from. And now I will discuss the approach that we have to modeling the food supply chain. But it can be applied to any supply chain, just-in-time products such as, I'm focusing on dairy, but produce, medicine, semiconductors, or other vital commodities, chemicals, radioisotopes, etc. So this is a long introduction, kind of, why it's important to take disruptions to supply chains very seriously. Okay, so let me start why it's important to model the supply chains. Bottom line up front, BLUF. Dynamic models have recently been recognized as a suitable tool to observe and predict supply chain behaviors over time. Such models, the food industry can test events such as the effect of human or animal pandemics on the supply chain and test also mitigation scenarios. And that's really the strength of this type of modeling. Now, modeling has been used extensively by governments, right, in deciding on strategies to pursue in mitigating the effects of COVID-19. We all know the effort that has gone into predicting the direction the pandemic will go on, in terms of its spreading. Principally, I would say that these have been epidemiological models aimed at understanding the spread of the disease and the impacts of different interventions, not really so much on supply chain, which has been severely affected across many industries. For example, the Institute of Health Metrics and Evaluation, IHME, an independent global health researcher at the University of Washington Research Center, has done very important research to predict the number of fatalities in the United States. Although, because of the vaccine, things are looking up right now. I would say 14% in the US are presently food insecure, which is still obviously way too high. I'm sorry, it's not 15%, I think it's closer to 14%. And 1 in 5 children. So it's still, too many people are going hungry, and there's, still too many problems because of this. So modeling the supply chain risks are critical for planning and for rapid response. So I should say that this work was inspired by a really pioneering publication by Andrew Huff and company from the EcoHealth Alliance in 2015, which attempted to do system dynamic simulations, which is also what I'm using, of the pandemic, and predict how many people would go hungry and for how many days. So the study was from 2015, predicting severe effects from the pandemic. It's too bad nobody took this paper seriously enough to do better planning. The paper stated that the Ebola epidemic that began in 2014 has caused severe food shortages in West Africa, which are similar to the effect that this model predicts in the United States. The likely effects of the reduction in the amount of available food are difficult to actually predict. However, it is likely to have severe negative consequences on society. As we've seen, the resilience of the food system must be improved against this hazard and others. So actually, the modeling is based on a field of mathematics called system dynamics, which is a kind of simplistic way of looking at the flow of objects, whether it's commodities or, say, CO2 in climate modeling, or many other applications. In fact, the easiest, most intuitive way of thinking about this is the typical hydraulic metaphor, which is a bath that has an inflow and an outflow and a valve that controls the flow in and out of the bathtub. It was John Sterman from MIT who actually invented this. And I figured he must be sitting in a bathtub when he thought of this. I looked it up. By the way, Archimedes didn't actually make his Eureka discovery in a bathtub. That appears to be a myth. So just so you know. Interestingly, the hydraulic metaphor is actually used in many different fields. So by hydraulic metaphor, I'm talking about, the water metaphor. And when you think about electric currents or circuits or transistors, it's kind of the same metaphor of water flowing is used. So now you can imagine that this kind of metaphor, flow of input of products and so on, can be applied to the field of the movement of commodities and supply chain, and really in the business field. And this is exactly the type of modeling that the EcoHealth Alliance used. So the model considers basically product flow from farm to table as a chain of connected compartments, buckets essentially, farmer to producer to distributor to retailer to consumer, that need to be maintained at a certain level to satisfy demand, right? And if the demand changes abruptly, then that has to be communicated along this huge chain of nodes, essentially. So some of my students will know my fondness for buckets. It's actually a metaphor which you can use for radioactive decay and branching decays as well. So I use this metaphor often. So however, the compartments are being depleted by the lack of product, resources, problems with transport caused by worker absenteeism due to pandemic and so on. And the model kind of keeps track of the total amount of food available at different stages of production throughout the supply chain as commodities in various stages of production, as they kind of flow through the different buckets. Now, the EcoHealth Alliance model from 2015 had a different objective, as it was not applied to specific cases. It also did not really appear to have a support of a partner in industry to do a really reliable estimation or a specific estimation. I don't want to take anything away from this fantastic model that they produced and the paper, and I really encourage you, if you're interested in this topic, to look at the paper. We decided to take a slightly different angle, which is to design a model for very specific food industry that could be affected by the pandemic, a very specific case, and to model it as something known as a digital twin. A digital twin is a virtual representation that serves as a real-time digital counterpart of a physical object or process. Though the concept actually originated earlier from spaceflight from NASA in an attempt to improve the physical model simulation of spacecraft in 2010. In some sense, that's my physics perspective, it's not very different from a Monte Carlo approach, simulation of physical events. The statistics is also there, and it's just a point of trying to produce a replica of a particular event or let's say a supply chain. So a digital twin model allows stress testing the supply chain due to operational and disruptional risks in order to calculate the effect of disruptions, as well as a plan for mitigation measures, which is what's so powerful about this technique. Back in 2019, the Gartner company, that's very futuristic, and they always list their top strategic technology trends, and they listed digital twins as one of their top 10 emerging technologies for 2019. So as a proof of principle, we developed a kind of hypothetical dairy supply chain model, which would be a digital twin of an existing supply chain. It includes 210 independent nodes, customers, distribution centers, farmers, etc. And the model allows us to test what the effect is of the pandemic, given a variety of disruptions and mitigation measures, and kind of build resilient networks because the goal is to build resilient networks that can serve underserved communities, especially during challenging times as we are in now. So the digital twin model of the supply chain is enormously powerful. It allows us to plan for disruptions in supply chains, to rapidly respond to crisis, which are kind of showing here in kind of blue backgrounds. For example, what happens if nodes in the supply chain decrease production due to the pandemic? How do we deal with rapid shifts in demand? What effect are some mitigation scenarios? And the nice thing is that you can try before you actually carry it out, try before you buy, right? You can try it in the digital twin before you carry it out, which has all kinds of risks associated with it. And so that's another power of this modeling, is that it's really any supply chain. If you want to disrupt the supply chain in some way to see if it has a positive benefit, then you can do that with a model like this, where you can test out different products or different different, being involved with different factories and all that kind of stuff. So outside of a crisis, it gives many other possibilities to optimize the supply chain. These are kind of the pink backgrounds. So this is kind of, it's a very powerful technique to kind of model the supply chain and really test it for different things. All right, so many different companies use the software. We use it for modeling supply chain and other aspects of the system. It was used in Bavaria for vaccine delivery planning just a few weeks ago when I wrote this. Procter & Gamble used it to model 20,000 distribution points across Indonesia, which is particularly complex with so many islands, right? However, at this time, you can kind of see that here, how it's modeled, right? You see Indonesia with all the islands, and if you want to bring P&G's products to different locations, that's enormously complex system to be able to accomplish. However, at this point in time, to our knowledge, few to none are actually applying this simulation technology to agricultural commodities, especially fluid milk and cheeses and these kinds of products. So this is where I decided to kind of apply it. So to test some of the digital twin ideas, similar to the EcoHealth Alliance model, we simulated a hypothetical 210-point network of a supply chain for 3 different products: fluid milk, cheese, large and small, and I'll explain why I chose large and small, exported from across California, US, Canada, Mexico, and Taiwan. And each green node, there's 47 of them actually, represent 10 farms each. And there are 4 California processors, and then various distribution centers and customers. The customers here are going to be the food banks, the school programs, what I call grocery cities, so this cities where you get groceries, and the restaurants, which were all severely affected due to the pandemic. The bracket shows how many nodes are simulated for various types of customers, but are all in different locations across geographical regions. And I'll show you the map. For example, there are 10 in Taiwan. And this model is applied to cheese, milk in this model, but can be applied to any other current or future just-in-time dairy products or any kind of product, really. The other strength of this is the model can be as complicated as wanted. As you know, at one point it's going to be a total big data project where you have many nodes and many interactions between nodes, and it's really a matter of how sophisticated how good your computer is going to be to actually do the number crunching. But you'll need a good system to produce a digital twin of a company's supply chain. All right, so these calculations that we assume, it assumes a certain expected demand, and I obtained this from open access information and talking with my colleagues, but it's very notional, right? A certain inventory policy, for example, distribution center can order new supply when it's below a certain stock. It uses different vehicles for transport depending on the case. So, for example, a milk tanker truck, what you often see, or other types of truck, ship, airplane, etc. All this is simulated in this system. The calculation assumes 2 principal periods: before global lockdown and after lockdown. And you can kind of think of each node acting as a little factory, a separate calculation of inflow and outflow, depending on the inventory policy, stock, etc., and the type of node, etc. So in this case, you see the GIF is a Safeway in Tracy, California, not far from Davis, California, where my colleagues are. And you can see the date in the left top corner, and the numbers change in blue, representing the product moving in and moving out of this particular distribution center. You can see that in the GIF, you see the date here change. Okay, so here we can see the hypothetical 210 node supply chain in action. You can see the various nodes. The green represents the 10 farmers, yellow, brown, a processor, or other ones are going to be distribution centers and hypothetical customers, as I mentioned before. And first, I'm going to kind of zoom in Fresno, California, the processing center, and then I'm going to zoom out, and you'll see the little vehicles during the day traveling across the country with little purple dots. So I'm going to just show you this. Oops, I'm sorry. Oh, this better work. Yeah, okay, so it's working. This cute little video. So here we are zoomed in on Fresno, California, where there's one processing center, and my computer is a little bit slow, but you can see this is all, zooming outward out of California. The green, again, are the farmer distribution points. The red are other distributors. The kind of brownish are the processors. Now you can see those little guys moving all across. I don't know if you can should see this, but those are the trucks moving across the country. Excuse me. I better drink some milk. And I'm zooming out now across, and there, okay, I'm also supplying towards Mexico and towards Canada, particular spots. And now, as I'm going to move across the ocean towards Taiwan, where there are also customers, and they would be customers for cheese, not for milk, of course, because that would be impossible. So it kind of gives you a sense of what this software is doing, which is trying to model the movement of all these products through the supply chain, the transportation, and then you can also affect the transportation by changing different variables and so on because of the pandemic. So these are the scenarios that we simulated in our kind of toy model. The no COVID case, and then the COVID case, which is steady production until March 2020, rapid increase in demand for several weeks, and then immediate shutdown in demand of school meal programs, then reduction in restaurants, and rapid increase in demand in food banks. So these are the kind of, you can kind of see how there's this imbalance trying to balance itself throughout the supply chain. Then I also model COVID plus, which I call it COVID plus, which is a random shutdown of activities of 3 processors from March to December, random shutdowns of distribution centers in Canada and Mexico. I will also simulate the prevention of ships docking in the port of Keelung in Taiwan, preventing goods to go to the Taiwanese market. And many more disruptional scenarios are also simulated. So in this case, we simulate the prevention of ships docking in the port of Keelung, preventing cheese to go to the Taiwanese market. During the pandemic, cargo ships are actually prevented in docking. It mostly focused on people rather than the cargo itself, but it still meant that those ships could not dock. The first node represents the port which is going to be in red, accepting the products. And then I'm going to kind of show you this. Then in this scenario on January 20th, the node turns gray, which means it goes offline. Let's see if I can get this moving now. Okay. Yeah, there you can kind of see what's happening. The node is going to turn gray, which is going to turn offline. And I'm going to zoom in on the factory. Okay, that's the port of Keelung. And when it turns gray, it actually, no products are going to be moving into it. And then 14 days later, it's going to turn on again. Anyway, so this could really wreak havoc on the supply chain by preventing ships from being able to dock, as we know from just a few weeks ago in what happened in the Suez Canal. Sadly, many seafarers were unable to go on land or even visit family during the worst of the pandemic. For months and months, these poor people had to be on ships when they were expecting to have, a proper leave. And they continued to work, which took an awful toll on them, and some even committed suicide because of their sadness. So here are some examples of mitigation measures that we've simulated and we can simulate. For example, in the case of high demand at food banks for small packaging cheese, we could consider cutting cheese blocks that go to restaurants. So big blocks of cheese that are usually sent to restaurants and then package them in smaller sizes. Another case is high demand in dairy products, but with limited freezers available, it's a problem. In this case, we could model government purchased reefer trucks that could be temporarily stationed at food banks, or a change to long shelf life milk, which, for example, there is in Asia and also in Europe, which can be stored at room temperature to account for high demand for milk without refrigeration storage. So we can simulate these different scenarios and mitigation measures without actually enacting it. That's really the power here, is that you have this complex replica of the supply chain, including, and you can go as detailed as you want in terms of, you can model also what happens inside a factory. And you can, you know, if a factory goes offline or something like this, all of this stuff you can model, and you can also model different processes of production. And so you can see what the effect is on the supply chain before actually enacting it. And that's really the power here. So for example, there's some interest right now in using this maybe for blockchain or something like this. And so the cool thing is that potentially what you could do is you could use this kind of model to see what the effect is if you convert part of a particular supply chain to use blockchain. What is the potential effect going to be on the supply chain, and can you do that in an effective way? So we're still developing metrics, I should say, but we use this one, which is order service level, to simulate a change in service during the pandemic. This is a measure similar to the number of hungry people, which is kind of what the EcoHealth Alliance used. The premise is that if orders can't keep up, the orders will not be able to get to the people, right? So the order service level is the on-time orders divided by the number of orders, regardless if they're successful, strictly the on-time orders divided by the on-time and delayed orders. And the number of on-time orders are the number of orders that were delivered within the expected lead time, and the number of outgoing orders are the sum of the on-time and delayed orders. And we see that in the no COVID case, the OSL, you know, that's this particular metric, remains essentially the same except later on. Right? So how does the service level change because of COVID plus? We see that there's significant disruption when we include COVID and the various disruptions when certain nodes shut down. You can see how the graph changes. Kind of summarize some of these results in you know, in a table. This is preliminary, but in this hypothetical 210 node supply chain system, we're predicting that the on-time service level will decrease about 5%, 10% for COVID-19 demand changes, which is, you know, dramatic when you think about the effect on a company and so on. And if we assume that the pandemic gets worse or got worse, then we can get as much as a 30% disruption, which is consistent with the EcoHealth Alliance. If you consider the number of hungry people metric that the EcoHealth Alliance use metric to be equivalent. We can also model mitigation efforts, rapid retooling to cut large blocks of cheese and provide the food banks. And preliminary estimates show that there's some improvement, but this needs to be tuned again with better realistic data. So you really have to have a strong industrial partner to be able to produce a digital twin. So numerical estimates and further analysis gives a sense of the effect, and it can be used for forecasting and planning mitigation strategies. Okay, so let me just have the conclusions. In a pandemic, segments of population may not get access to vital dairy products. We find that if the situation gets worse with multiple nodes being taken down intermittently, about a 30% reduction in service level from the no COVID case. This model can be applied to the impacts of animal, plant, and human pandemics and other disasters on dairy farm supply chains as well. And furthermore, we shouldn't assume that no other catastrophic events will not happen. Like, we were very lucky, right? During this time in California, there was no earthquake. There were no severe other catastrophic events that happen. They did happen across the world, right? At the same time, earthquake or snowstorm, etc. All these things can happen together. And so it's important to plan for it together during a pandemic. This software under the guidance, especially of UC Davis, can also help design and put in place the One Health Sustainable Agricultural Community Network. One Health, and this is a quote from a paper written by my colleagues, One Health is the concept that the health of humans, animals, and the environment are inextricably linked. And this approach can be applied to food safety, sustainable food production, and environmental stewardship by bringing together interdisciplinary teams to create a network, a One Health network, to address these challenges. Any questions about that? I'm just going to point back at Rich. You can answer those. But the challenge to these simulations is that they, kind of emphasize this. They require detailed data and a trusted partner to do this carefully to produce a digital twin, which is again your replica of a supply chain. It's a strong commitment from partners. So this pandemic, as bad as it is not the worst, and we really need to plan for the next one. As the president of the EcoHealth Alliance, Dr. Peter Daszak, warned after SARS, right after SARS, that the next is this amazing quote by him: the next pandemic could be harder to detect, but more deadly than this one. And that was a long time ago. And it's too bad we didn't learn and prepare for that.